Hello, this is Pankaj Mehra from Samsung Electronics. I'm VP of Storage Pathfinding function in the Memory Business Unit. And today my topic is emerging data-centric storage architectures. Here I'm going to talk to you about some of the more advanced workload optimized SSDs that we are working on with the idea of addressing the market for data at large scale. So let's begin by identifying what are the principal considerations that you face when you're dealing with data in the scale of hundreds of terabytes or petabytes to all the way to exabyte scale data lakes and media processing. So first thing is, you want your processing power and processing bandwidth to not bottleneck. Because to handle data at scale, you need the ability to process and move that data to the processing that scales with the data. Second, when you have that much data, you inevitably end up with a very large number of objects. And if the metadata that you have is too granular or insufficiently granular, then you will end up with metadata inefficiencies and resulting write amplifications and other consequences. Thirdly, in some of the infrastructure trends, what's going on is we are disaggregating now storage from compute nodes which want to be increasingly stateless and moving towards an architecture where our storage is network connected, meaning connected to the data center fabric, for instance. Okay. In this case, the choice of protocol inevitably revolves around something like NVMe over Fabric. It could be NVMe over TCP or NVMe over Rocky, for example. And the question is how many times where, for instance, you should be terminating that wire protocol. And we'll notice that in current architectures, you can have bottlenecks due to repeated termination of protocols, buffering and rebuffering, which leads to latencies and pipeline bubbles. Okay, so that idea of noticing that bottlenecks lead to inefficiencies then lead us to the content on the right side of the slide that you see, which is that if you have these bottlenecks on processing power and processing bandwidth, then you find it difficult to deliver both performance and scale. The reason is that as you start adding more and more content or more and more data to your system, then either the processing bandwidth or the processing its power itself, they fail to keep up. For example, they may roofline. If you are not careful with how you organize your storage, you may end up repeatedly moving the data and having high write amplification. This results in wasted endurance, shortening the lifetime of your flash storage, which has a pretty direct impact on the cost of infrastructure. If you move data in more than necessary, then you could end up wasting, for example, either front-end memory bandwidth in your storage array, or if you are going through the host and repeatedly copying data through the host CPU's memory, then you end up wasting L2 memory bandwidth, for instance. Finally, storage is in the I/O realm, and we have to look at the CPU overheads of I/O and CPU overheads of virtualizing that I/O. These are some other sources of inefficiency that we want to keep that efficient and largely away from the CPU to the extent possible. Okay? So these problems are not unknown to the community. The problem, though, is that the ideas that we have all been at system and software level. And these ideas are mature. They have been around for almost 25 years. For example, disaggregated storage is at least as old as fiber channel when we started to separate storage and networking, when we started to unify storage and networking and tried to move our peripherals over the network. So we built fiber channel initially. These days, we have more unified data center fabrics. We're trying to move storage to work over Ethernet and TCP, etc. And now the next thing is that we want that to move from system and software level into the SSD level. So the idea of Ethernet attached SSD is reflecting the fact that we are working with disaggregated storage that wants to terminate once at the SSD. Likewise, the idea of computational storage is as old as active disks, meaning it predates even large use of flash memory in enterprise and data center. Okay, so for instance, computational storage was practiced in tandem mainframes, where we had executor in DP2 and similar concepts for taking a piece of a query plan and executing that near hard disk. But the idea was at system and software level, same as with disaggregated storage. Okay. Now with things like smart SSD and other forms of new computational storage, we are noticing that this idea is ready to move into the SSD. The third idea is a little bit more familiar to the industry. This is the idea of object storage or key value storage devices. It's an idea that originated with the work of Garth Gibson at CMU. And then there have been several efforts in SNIA and also in various companies to try and build object storage devices. So the latest in these is, of course, KV-SSDs and its new protocol and command set in NVMe, and then the associated APIs in SNIA, all of which are now mature, and we are, starting to look at second generation devices that are more native key value devices. So summarizing, we are revisiting some old ideas here, but in a new way. Okay, we're revisiting three major ideas that are 25-year-old, and in 2020 we are looking at them in the context of implementing these ideas at SSD level rather than at system and software level. So let's look at the first of these, which is computational storage. Okay, so Samsung's Smart SSD computational storage device is designed to accelerate data-rich workloads. Okay, and the way that we have engineered the platform is with its own internal data path, meaning with its own internal bandwidth, and internal compute resources in the form of a Xilinx FPGA that is built into every Samsung Smart SSD. So the SSD still has a controller for doing the normal FTL and GC and other functions, and for managing backend management of NAND, of which we have 4 terabyte of our VNAND. And then the FPGA, in addition to having the FTL memory that the controller has, the FPGA has its own dedicated DRAM. This can be used for either IO buffers, or if you're doing multipass sorts or other DRAM-oriented operations on the FPGA, you can use this DRAM, as well as you can use that for moving data between host and FPGA, for instance. So the device that we have is capable of 3 and 6 gigabytes per second internal bandwidth. The FPGA has about between 3 and 10 cores equivalents of offload or acceleration capability. Like I said, it has 4 terabytes of flash storage and 4 gigabytes of FPGA attached DRAM. Okay. In the middle, we illustrate the principles by which this device works. Okay. So as you notice that, as you increase the number of devices in existing systems, one of the problems we are seeing, whether it is in database appliances or media servers or media appliances, is after 4 or before definitely 8 SSDs in a single 2-socket server, you start to hit some kind of a roof line on performance. Okay? Your performance does not scale with the number of modern SSDs in the system. And this causes a problem that there is a net x86 tax on data today, which is you're having to either scale out or having to build new arrays even before you have used the full bandwidth of all the devices in the system. And so with this new architecture, what we are trying to do is we are trying to, A, not have that roof line and have linear scaling with the amount of data in the system. And second, what we are trying to do is you're trying to do this at a higher slope than the original curve by having this internal data path that keeps data out of caches where they might pollute or they might destroy TLB entries on the CPU or end up using tying up memory resources on the host. So by doing that, we want to do this scaling at a better slope than in the traditional architecture in which all data is poured out of the SSDs to be processed. Okay? So these principles are basically near data processing where you can do things like format conversions from Parquet, for instance, filtering of data, metadata management, whether it is for media objects or for database objects, analytics such as aggregation, or video processing operations such as transcoding or other video analytic operations such as object detection near the data and at scale and scaling with the amount of data in the system. As well, you can use this opportunity to, for example, handle content more securely within the device rather than having it pulled out where multiple VMs have access to the system or you have open buses. Or edge acceleration, where you may use the same idea of near data processing, but not for taming scale out, but rather for taming a different kind of scaling issue, which is north-south scaling, where you have many servers, one after the other, handling media content, and you can use this kind of devices to consolidate the work of many servers into one, thereby limiting the latency that is wasted handling video content from server to server or gaming content from server to server. Okay? So these result in then latency benefits. On the right, we show an illustration of some of these benefits that have been created by various partner companies that have worked to port their IPs to the Smart SSD. The first of these is Bigstream, and we have several database partners in this area who are working with us very closely, companies like Swarm64 and others who are working on, for example, proprietary OEM and cloud databases to get them working on the Smart SSD. Okay, so over here you see that in the traditional SSD, you pull the data out of the SSD to process it. This takes time. Then, for example, at the leaf of a query plan, you may have filtering operations that are applied soon after you decompress the data. And then you have downstream processing such as joins or shuffles or such. Okay, so if you do this instead using the Smart SSD, and this is an actual trace on a TPCH query, you see that filtering and decompression are executed by these Smart SSDs FPGA in an accelerated fashion because this is highly parallel hardware style execution. So it goes much faster than traditional CPU-based execution. There is data reduction, which results in net less amount of data that has to be moved out of the SSD. And even if you do not accelerate that downstream processing, you still see 2 to 3x acceleration as shown here. If you do accelerate that downstream processing, for example, if you accelerate shuffles and sorts, you will see further reduction, and this will start to approach between 4 to 10x acceleration for databases, we anticipate. The second example in the right panel shows what happens when you take the same idea and apply it to video processing. Here, what we are showing is that a 2-socket server handling the video transcoding task, and its CPU utilization is shown in the red line, and its frames per second transcoding rate is shown in the silver gray. Okay, so you see that a 2-socket server, Xeon server, is capable of about 780 frames per second, 720p, H.264 transcoding. Beyond that, the performance is rooflining, and you don't see much improvement in performance even as you increase the number of devices in the system. With the Smart SSD and internal compute and bandwidth resources, performance keeps scaling as you have more and more devices in the systems. By the time you have 3 or 4 devices in the system, you're starting to accelerate beyond what a 2-socket server could have handled. And we project that as you do this because of the extremely low CPU utilization when you use smart SSDs. There really are no bottlenecks in the system, and you could easily scale to 16 or 24 devices in a single media server. At the bottom, we are showing what happens when you take a traditional storage service task, such as compression, decompression. And here, we have worked with the partner company Identicom. On the video, we have worked with the partner company CTXL in China, Hong Kong. And then on the bottom, we are showing our work with partner company Identicom on high compression rate data compression for storage. And what you see here is that it is possible using smart SSDs working in parallel to achieve near line rate throughput on compression and decompression tasks and achieve extremely high PCI and CPU efficiency, as well as really useful host memory latency. You rarely do a compression or decompression task alone. The downstream operations need the CPU power. And by doing this kind of work, you can both offload additional operations, such as we shown in the top panel, and additional surveying or analysis tasks that you need to do depending on whether it's database or video workload, not just compression or decompression. So there are more use cases. For example, within databases, we are not just working with Spark on BigStream. Like I mentioned, we are working on PostgreSQL with a couple of vendors. We also have engagements going on with our cloud customers and with industry software partners to port to other databases to our devices, some that are named here and some that are not named here. Okay. The general architecture we are following in analytics acceleration is shown here. Okay. And this could be over a wide area network or could be within a data center. So generally, storage architecture for data at scale starts with some sort of a blob storage layer at the back. This might be serving up blobs into a NoSQL database, such as Cassandra, or it might be serving it into a traditional relational database, such as Postgres, or an in-memory oriented compute layer, such as Spark. Okay, it doesn't matter. Wherever your compute is, your data inevitably is in high efficiency blob storage. Okay, and your compute nodes that are going to work on that data are trying to be, in the style of throwing as much iron at the problem as possible. So they are trying to be stateless, okay, or at least be very ephemeral in the amount of data they hold near the CPUs. So, the scale of data in a typical data at scale situation is that you will have hundreds of terabytes bordering to petabytes in the bottom tier, which is the primary storage tier. You will have single-digit terabytes on the compute nodes, just doing minimal caching near the CPUs. And the gap between single-digit terabyte and double-digit terabytes is then bridged by this new family of accelerated cache nodes, such as you have seen from Amazon, the Aqua node. You will see this more and more, this idea of accelerated cache nodes that have both an accelerator, such as FPGA, and SSDs, where you hold the data for fast, high-speed operations. What the smart SSD does for these accelerated cache nodes is it combines the acceleration resources and the SSD resources in such a way that you can have that linear scaling that I showed you before. Okay. In addition to all this, there are additional use cases that are still emerging. An example is shown on the right here in the case of searching of stored data. So you can imagine that, if you have very large amount of security data, such as various kind of fraud or security-oriented logs, as is common, and you want to search them in parallel very quickly, delivering predictable performance irrespective of the complexity of expressions or the amount of data. And what is shown here is the work of another partner in the industry who is working with government customers. They built appliances with 24 of our smart SSDs in a single server that can scan at 60 gigabytes per second per device, per server. So 24 devices and a single server scanning at 60 gigabytes per second, and with much better performance characteristic, both higher throughput and low jitter compared to a CPU-based software solution for the same problem of regular expression searching. So in terms of our roadmap, we are now starting to work on our second generation devices. And we are very interested in talking to our customers about their requirements for integration of acceleration, the interfaces, software and hardware that they want, form factors for how they want to fit these devices into their infrastructure, and the workloads that they want to accelerate. At the same time, the experience we have gathered from the first generation Smart SSD, which as I mentioned, is a 4 terabyte device with about 500,000 LUTs. We are translating those best practices into our work with SNIA and NVMe protocol groups. We have had some good buy-in from major customers in the industry whose logos are shown here. And as we work on the second generation device, we are very interested in broadening the ecosystem as well as broadening the set of use cases in order to see computational storage deploy much more broadly in the infrastructure. The second idea I want to talk to you today is about SSDs for disaggregated storage. Okay, here, if we look at the situation, for example, about a year ago, we were starting to put together these disaggregated storage nodes in which SSDs were fronted by 2-socket Xeons, for example, with say 300 gigabit Ethernet adapters. This is actual configuration from one of the test chassis that we built here at Samsung. Okay, when SSDs were still slow, the front ends could sort of keep up with the amount of data generated by the typical number of SSDs in a storage chassis, for example, 24. As the SSD speeds have picked up with the arrival of PCI 4 or PCI Gen 3 by 8, for example, SSDs can now deliver almost 150 gigabytes a second of data from 24 SSDs. The front-end architecture has various limitations, not just in terms of the interfaces, but also the compute power and the packet handling at that interfaces. In the original architecture, we were terminating the protocol in front of the devices. So for example, with the NVMe over Fabric protocol, in the conventional JBOF, just a bunch of flash architecture, the protocol was terminated at something like a ConnectX 5 part or a Stingray part. And then behind that, over a PCI switch, you were taking the capsules out from the Fabric protocol data and feeding them as standard NVMe commands back to the SSDs. This unnecessary layer of protocol termination with the associated buffering, memory management, so on, are challenging front-end systems in a way that is completely unnecessary. There is very clear evidence of that this architecture is not scalable to the high-performance modern SSD at the counts that modern storage chassis wants. So more and more, we are working with the industry on a single termination architecture in which the NVMe over Fabric protocol, which is the synonymous with over the Fabric disaggregation in the data center, terminates at the SSD itself. And we can go to a more conventional switch-based architecture in front of those SSDs. We still have several issues to work out in this architecture in the area of security and manageability, but the benefits we get from this architecture are high bandwidth, linear scaling, same as with Smart SSD, lower power due to fewer protocol terminations, and lower latency for the same reasons. Okay, so for disaggregated storage, we are working on an idea with the intent of delivering these devices in a couple of years for these new kind of chassis that we call Ethernet bunch of flash. And we are working on this together with our customers and partners. So the first of these devices that we built, we built with two 25 gig interfaces. These are successfully used in our work with ecosystem partners in data center fabric networking space to identify what is the key items of work in terms of managing fabric congestion, and in terms of manageability and security. So these POCs are now informing our second generation work, as well as here again, we are interested in working with customers on their requirements in terms of their choice of fabric protocol, their intent to do hardware offloads, the joint work with the community on form factors, and working closely with networking community on the prevalent approaches for congestion control in data center fabrics, as well as working with end customers and infrastructure owners on security and management principles that are best suited for Ethernet SSD. Okay. Lastly, today, I want to cover the basic architecture of object storage. And as you know, object storage is synonymous with infrastructure, storage infrastructure at scale. Okay. As was clear even in the smart SSD slide I showed you with accelerated caches. But these days we see object storage principles being applied all the way from secondary storage tier to primary storage tier. Inevitably, storage for virtual machines is constructed out of something that looks like an object storage tier. And also because of the use of compaction and other principles in both databases and storage for virtual machines, object storage penetrates primary storage tier in the cloud, as we well know, for scalability. So the problem with traditional storage has been, meaning using block storage under object storage, has been the same sort of scaling problem, which is shown here with a NoSQL database, RocksDB. And what we did for this comparison is we took our traditional data center SSDs, such as PM983, in one case running block firmware, and in another case running KV firmware. And we compared the application performance just by comparing the interfaces that are used in moving those block level data structures. So as you can see, what happens to objects as you use block protocol is that the objects get spread all over the place and your performance saturates. With the key value SSD, the SSD has ability to internally organize that data much better and to internally translate those block operations in such a way that the external entities such as CPU and DRAM see much more contiguous data, do object level storage and retrieval rather than block level storage and retrieval. Just the overhead of metadata and the segmentation and assembly of objects that has to be done in the software level. Offloading that overhead results in a much efficient CPU model, which is behind the performance that you see here. With the number of these key value SSDs in a system, you can see that the transaction and retrieval performance of RocksDB starts to scale linearly with the number of devices in the system. Okay, so as opposed to traditional approach of handling metadata and the translation from object to block in software, the KV interface and the KV SSD give you a much more CPU-friendly interface. These benefits are then visible as latency benefits, as shown in the top left in the slide. For this database, which is RocksDB, that is optimized for KV. This is KV Rocks work that was done at Samsung, showing 60% better latency on the common workloads that we have in the data center, such as random updates. And then on the insert heavy operations, you see higher throughput and more steady throughput from KV SSD principles than compared to traditional ROCs on. But the most pronounced benefits are in the area of write amplification factor. By giving the device the freedom to know what is read and written together, you can avoid unnecessary copying of data during garbage collection. It's one of the most application level ways of managing storage that we are aware of. The benefit is really pronounced. Basically, 11x less bytes written translate into 11x on capex of endurance-oriented lifetime of SSDs with KV SSD versus traditional SSD. Okay. So here again, like I said, that we have first generation devices out there for a couple of years now. And then, we have open sourced the stack principles for how to organize your stacks to take advantage of these new APIs. And we are interested in understanding your constraints, your requirements, your typical metadata and data sizes within those objects, your desire for interfaces, form factors, and workloads as we develop subsequent products in this area. Okay. So finally, what I would like to do is walk through some of the benefits of the technologies I talked about today, as well as some work we are doing that I didn't get a chance to cover today. Okay. So first thing is that both, as I was mentioning with key value SSD, where you are informing the device about the access pattern of what is read and written together. Same thing with smart SSD. You're informing the device about the formats, whether it is Parquet or ORC or CSV, that your data is in, so that the device can help you with filtering. Just imagine the benefit if you're retrieving data for 1 out of 10,000 regions. And if you had to extract all that data only to throw away 99.99% of that data, if you could then just offload that filtering operation to the SSD, and if it understands your data format and can apply the filtering operation, you achieve significant data reduction. That is but one of the benefits. You can create histograms, you can sort data, you can do a variety of technical and business functions on the SSD once you make it aware of what is it that you have stored and what is it that you're trying to do. This work is actually picking up steam in the industry in both SNIA and NVMe these days, with new TPARs being written and new APIs for computational storage being discussed. Acceleration is a natural follow-up of application awareness, which is, as opposed to doing the work at the speed of software, if you can translate loopy operations on structured data, whether it is matrices or tables, you can imagine that hardware can apply its native parallelism, whether it's using FPGAs or other constructs in hardware, and can deliver that data processing much faster, not just from what it does internally, but also from the basic architecture of something like smart SSD, which knows how to execute operations on data in parallel. Which is a fairly well understood concept by now. We have 40 years of databases knowing how to do filter pushdown to something smart. And this is very present in layers such as Spark, where filter pushdown is routinely exercised, for example, in a distributed system context. If we now view each server as a heterogeneous distributed system and view each smart device as basically a microserver in its own right, then the server knows already, the database software on the server knows already how to do that push down to an intelligent device. So we are just, riding the maturity of software here with these new device principles that bring a new level of performance and scaling into the data center with the smart SSD, for instance. Okay. And then, once you start processing data internally, you can imagine that the benefits, like we were showing with KV and smart SSD, you're not streaming data through your L2 caches. That means the real work of the CPU in terms of business logic, it stays in the CPU. Its data stays populated in the caches as opposed to getting bulldozed by all the streaming data that you would have pushed through the CPUs. So by leaving that data and doing near data processing, you free up the CPU and reduce data-related CPU load. As we saw with the KV SSD and elsewhere, we have shown with our zone namespace work that we can improve write endurance through application awareness and workload intent being communicated to SSDs. With the Ethernet SSD and with the smart SSD, if we talk if we eliminate the number of times data has to be staged on its way from where the media where it is stored to the CPU where the results are needed, we reduce we reduce pipeline bubbles and then improve throughput. So with smart SSD, this happens because you're able to talk a more mature protocol such as Arrow. The same protocol that you talk to a distributed system, you can talk to something like a smart SSD, okay? Even though you're working with Parquet data that is stored in a block-oriented device. With the Ethernet SSD, the same idea, but in a different shape. You have disaggregated storage. You know that you're going to go from NVMe over Fabric, and then you're going to have to execute those command capsules. The fewer times you terminate and then reissue that storage protocol, the more efficient from a latency and throughput perspective your architecture is going to be. So that's what our work on Ethernet SSD is for very traditional disaggregated block storage, whereas the work on smart SSD is fewer terminations at the application layer. Then, you know, we didn't go into the zone namespaces today. So let me skip over that and talk about fewer stack translations. So when we were discussing, you know, KV SSD, normally you would be translating from key value references into logical block references to physical block references in storage. This idea has been around in the industry for a while, that if you could eliminate the translation through that logical block address layer and go from key value to whatever the native flash needs in terms of physical addresses, those fewer stack translations have similar benefits as fewer protocol translation. And we discussed, in case of KV-SSD, the metadata optimizations, meaning awareness of which objects are stored and retrieved together, helps align garbage collection and hot code storage of data toward reduced write amplification benefit. Okay. In all of the devices, one of the things we are seeing is that as you add data in the system, which is the primary challenge of managing data at scale, your principal need is to be able to build larger and larger nodes with fewer and fewer overheads. We talked about the x86 tax on data. Basically, Samsung innovations on workload optimized SSDs are giving you the basic technology, whether it is for your disaggregated storage or for your data intensive workloads or media intensive workloads, or for object storage that you're trying to build at the scale of 10,000 way scale out today. We're trying to give you a way to tame that scale out and reduce that x86 tax on data, so you can manage more data using fewer CPUs and fewer front ends, and your data bandwidth and performance can scale linearly with the amount of data in the system, which is the essential challenge that we have aimed for. So let me stop here, and during the live session, then we can take more questions. Thank you.